Good morning and welcome to all. We can start our webinar. For the ones who have already attended a build-up webinar, thanks again. We are pleased. Can you hear me? Good morning. Maybe we have to begin the presentation again, sorry. Welcome to all. We can start our webinar. And for the ones who has already attended a build-up webinar, thanks. We are pleased to organize these technical appointments. And instead, for people who has registered for the first time, let me spend only a few words for introducing BuildUp. BuildUp is an initiative by the European Commission since 2009, is an open collaborative portal born to disseminate the energy performance of building directive and to showcase the results and best practices coming from all the EU states. As editorial team, we invite you all to connect to BuildUp as visitors, but of course, we invite you to participate as active members of the community. We will be pleased to receive your contribution in the form of publication, news, best practices, a webinar, and to find the most appropriate way to showcase and publish your projects. Let me remind next webinar to be held in December about building renovation passport. This webinar will be realized in collaboration with Eurace, and you'll find on the home page the agenda and how to register. So again, I invite you to connect to find information for next webinar. Now let's focus on today's webinar that has been organized in collaboration with the Dr. Bob project, that is an H2020 project, facing the real-time optimization of the local energy production, consumption, and storage. So today we'll explore very challenging topics as the integration of renewable sources in block of buildings and the positive impact of smart services and ICT technologies. Only one note for the audience. If you have some questions, you can send us on the chat, typing on the chat, and we'll reserve a slot at the end of the webinar for questions and answers. Let's start our technical session. I leave the stage to Tracy Crosby that will provide us an overview of the project.
Hello everybody, thank you very much for joining us. I'm going to give you a very short introduction to the Dr. Bob project, which stands for Demand Response in Blocks of Buildings, and then I'm going to hand over to the people who've been involved in running our pilots. Yeah. So, okay. Just to let you know, the project has been running from March and will end next February, and we have 10 partners from 5 European countries and 4 demonstration sites. The key thing I wanted you to take away from today is the ongoing work at the demonstration sites, where we've actually implemented the tools that we've developed in the project. Okay, so demand response, as you know, involves consumers reducing or shifting their electricity usage during peak times in a response to time-based tariffs or other forms of financial incentives. The advantages of demand response are widely accepted. They include reducing the need for investment in reinforcing distribution networks, supporting the integration of renewables, and even increasing national energy security and so on. But the question then becomes, why are consumers and industry slow on the uptake of demand response? And the main aim of the Dr. Bob project was to demonstrate the economic and environmental benefits of demand response in blocks of buildings for all of the different kinds of actors required to bring it to market. And these include DNOs, energy retailers, TSOs, energy service companies, IT providers, aggregators, and facilities owners and managers. Yeah. So what we really wanted to show was what are the benefits for these stakeholders. So what we did was we developed a a solution, a demand response solution. And the key advantages of this was aggregation of the demand response potential of many blocks of buildings and the real-time optimization of local energy production, consumption and storage. User adjustable optimization criteria is also very important because some organizations, like universities, may be looking to reduce their carbon emissions, their CO2 emissions. But others will be looking in order to reduce their energy costs and to maximise profit. The solution that we've developed is also automated in that it adapts to fluctuations in energy demand and production, changing weather conditions and dynamic energy tariffs. So this is a diagram of the architecture that we've developed. It's a scalable cloud-based central management system supported by a local real-time energy management solution, which communicates with individual buildings, management systems, and generation and storage. Our solution was achieved by integrating a demand response manager from Siemens, a local energy manager system from Teesside University, and a consumer portal which was developed by Grid Pocket. Okay. The demand response manager provides the ability to aggregate demand response actions. The local energy manager provides energy management at the level of the block of buildings. And the EcoTrucks customer portal provides user interfaces for energy management. The solution is applicable at all voltage levels. The micro level optimized energy management to ensure the efficient use of aggregated assets is provided by Siemens DRM, while the LEM integrates with local generation and storage assets and building management systems to manage micro level supply and demand. Yeah. And next you should be able to see some of the interfaces and some of the functionality provided by the consumer portal developed by Grid Pocket. Okay. However, when we were thinking about our solution, we decided that to enable building owners and managers to assess the applicability of our solution to their block of buildings, they needed a method of assessing or validating the technology readiness of their building stock to participate in the Dr. Bob energy management solution. Yeah, so building owners have to be able to decide, are our buildings ready for the implementation of this solution? This is in harmony with other ongoing initiatives within Europe, yeah, where there are projects looking at smart readiness indicators for blocks of buildings. So what we did was we developed what we call demand response technology readiness levels to measure the technological readiness of a block of buildings to participate in a building stock orientated demand response program. Most of you will be very aware of the concept of TRL. Yeah. Okay, so operationalizing, oops, I've jumped a slide, apologies. Hopefully I can go back. Okay, so operationalizing the demand response technology readiness levels for blocks of buildings is in some ways self-explanatory, but technology refers to the building site energy and communication systems. It includes metering and telemetry, flexible load, local energy generation, and energy storage and plant. Readiness refers to time, i.e., are they ready for operations at the present time? Level refers to the extent of the capability of a block of buildings to take part in the Dr. Bob energy management solution. And block of buildings refers to a group of buildings that may or not be in proximity to each other if under common governance. Okay, so essentially what we did was we developed 4 levels. So it was DRTRL 0. This means that a building does not have the technical capacity to enable the implementation of the Dr. Bob solution. DRTRL 1 is a manual capability. A building site has flexibility and can be controlled in a manual way by facilities managers. DRTRL2 means it's partially automated. A building site has the minimum technology required to participate. And DRTRL3, I'll get it right this time, means that their buildings have full automated capability. Now, we have quite limited time during this webinar, so rather than detail what is required at each demand response technology readiness level, I'm pointing you to a paper which we have published and is available open source in the Buildings Journal, where all of the technical information can be found, and I hope you enjoy reading it. Now, at this point in the presentation, what I'd like to do is hand over to the people who've been in charge of running our pilot sites. The solution has been implemented at 4 pilot sites, and at each pilot site it was necessary to upgrade the demand response technology readiness level. And I will now hand over to our first pilot site operator, who can tell you about the implementation of the solution.
Hello, good morning, everyone. Thank you, Dr. Crosby, for the introduction. Let me advance through the slides. Yes, it appears to be working correctly. Okay, so for the next 5 or 6 minutes, I'd like to give an introduction to the Dr. Bob UK pilot site, along with my colleague, Dr. Rodriguez, who will be explaining some of the preliminary results that we've obtained from the demonstrations. So time is quite constrained, so I will advance straight away. So the UK pilot site, the demonstration site for our project, is part of the Teesside University main campus, which is located in a town called Middlesbrough. Middlesbrough is on the border between the northeast of England and North Yorkshire, halfway in between York and Newcastle, roughly, for anyone who knows the geography. The main campus where the demonstrations take place is situated just outside the town centre and roughly occupies an area of 3 hectares. The main campus is based on 33 separate buildings, most of which are teaching and administration, and 5 of which are townhouses and halls for the students. Overall, the term time occupancy is approximately 22,000. So if we look at the technical architecture implemented at the UK pilot site, as my colleague Dr. Crosby outlined in the introduction, there are 3 main components in the technical solution. The component which is the first component, which is cloud-based, is the demand response management system provided by Siemens, this BEMS component. We also have the consumer portal, which is located in the cloud as well. And local to the demonstration site is the energy management unit. Now, the energy management unit connects to all of the assets that are local to the demonstration site that enable demand response to take place. The main assets that we have is a frequency monitor, which provides real-time information via a local signal to the LEM. a gateway PC, which allows us to interact with the building management system for the campus. And we also have, via file transfer mechanism to a metering system server, access to real-time meetings from the electricity meters, which are gathered via a 3G, 4G infrastructure. So when demand response events occur, are processed by BEMS in the consumer portal, the local energy manager can take the required actions in order to implement the required demand response. So in terms of the pilot site demand response technology level, the initial TRL was 1, indicating that we could apply some manual controls, manual response to events, but we didn't have full automation. The implemented technology readiness level was 3. The main technical upgrades were the metering system was upgraded to give us better real-time measurements. The building management system was upgraded to enable control over the BACnet protocol. Also, another point which is missing from this little slide was we designed and implemented the frequency sensor to give us fast response to low frequency events. In total, for the demonstration at the Teesside site, we identified 5 different scenarios which were of interest. One is electric demand reduction during a certain period of time. The converse of 1 is 2, a commanded electricity demand increase. This can typically occur during summer months when there's an excess of PV. 2 scenarios related to peak demand reduction using explicit control and implicit controls. And the 4th is static frequency response. And you can see over the course of a year, we've responded to numerous types of each different scenario. So now on to a case study. If we look at the first scenario, demand reduction, short-term operating reserve in terms of the UK market. Well, when a demand response request arrives, some processing is carried out. Via the consumer portal, the facilities manager is given the opportunity to opt out if desired. If the demand response request is accepted, then we will typically have some time to prepare for the demand response event itself. The window itself is where we would implement the demand reduction, and after the event itself, we have settlement in terms of the financial aspect, which requires baselining throughout the course of the response event itself. So the architecture that was chosen for the implementation via the LEM, which in this case acts as an aggregator for lots of individual heating, ventilation, and air conditioning units, which are all under the control of intelligent thermostat units. The intelligent thermostat units perpetually run a dynamic programming procedure which acts as a predictive control. Further details can be found in a paper which will be delivered at the IEP conference in Oxford at Oxford University in March of next year. And in addition to the individual controls via the communications, we have an aggregation unit which selects certain weights to achieve coordinated demand response. The coordination procedure runs during the preparatory and active phases of the event itself. So looking now at some calibrated simulation results, we can see that in the absence of any demand response weighting, during a demand response window, there is no penalty applied to the electricity consumption. and we say the temperature of a building will cycle around its set point depending upon the settings of the algorithm, which behaves in effect as a relay. Now, if we look at a partial weight applied to electricity consumption during the DR window, we'll see that we can start to see reductions in electricity consumption. We can see that the chiller is on for a smaller fraction of the time during the window, and the penalty that's paid is deviations from the temperature set point, which obviously affects user thermal comfort. And if an even larger penalty is applied, we can completely switch off the chiller during the demand response event itself, and the expense is even greater, loss of thermal comfort, pardon me. And the procedure which selects for the weights in order to achieve a coordinated response finds the best trade-off, which achieves the required electricity reduction across multiple units, whilst simultaneously minimizing the thermal discomfort of the users. Again, technical details will be published in a subsequent journal paper. If we can now advance, whoops, gone one slide too far, to some preliminary experimental results. We can show that for an average Wednesday, the electricity consumption follows the lighter green line, and when a demand response event was reacted to, we can see a clear reduction in electricity consumption over the average, and the red trace during the demand response event window shows the shifted energy use. Okay, at this point, I would like to pass over to my colleague, Dr. Rodriguez, who will describe some preliminary results from some of the other scenarios that we've been experimenting with. Thanks very much for listening.
Thank you very much, Dr. Short. I will now go on and explain over the scenario 3A, what we call the scenario 3A, which is referred to the triads. The triads is one of the available demand response products in the UK market, electricity market, and refers to the transmission network use of service. What we call the triads refer actually to 3 periods of time across the year in which the clients are charged for 3 half-hourly periods, big amount of per kilowatt. So usually these periods of time, they are found retrospectively. They are the highest demand periods during the year. In the UK market, they occur during the winter, and especially between 5 p.m. and 7 p.m. When there's a grid warning, the users need to carry out a communication chain in order to perform the demand response event. In the case of the UK scenario, 3A, we are making use of 6 different buildings or facilities, which are the Clarendon building, some offices, some laboratories in the Middlesbrough Tower, the Constantine building, the laboratories in the Stevenson building, the EV chargers in the car park, and some offices in the Phoenix building. So this requires actually big coordination, a high level of coordination within the different stakeholders involved in the demand response event. Is partly automated but it also entitles and included some collaboration between different stakeholders. So what we have defined within the Dr. Bob UK demonstration is a kind of chain of control in which after the energy manager decides to opt in or opt out, he emails the team leaders who are organized within buildings. And these team leaders are in charge of, with a day in advance, they are in charge of organizing the schedule management, contacting the rest of the people in the building in order to encourage them to take actions within the demand response event, and also to make sure that the demand response event is conducted during the demand response as planned. So what we have defined is also that we have the market emulator, which has the historical data from the UK demand, electricity demand, and actually takes this and can forecast the demand for the next day, and therefore to predict a likely happening of a triad event. As I have mentioned, these triads are given afterwards by the grid. This is an example of an experimental case study that we have run here in the Middlesbrough Teesside University Middlesbrough campus, and we can see the yellow line here corresponds to the 14th of March, in which we ran two demand response events. One of the events took place from 12 to 2, and the other one ran from 4:30 in the evening until 6, I think. So we have taken the mean value of the electricity consumption within one of the buildings, which is the Clarendon building. You can see it here in the image, and we can actually appreciate the effectiveness of this demand response, which is larger, is greater during the period which corresponds to the afternoon, because actually the university tries it to happen in the tries to minimize the energy consumption in the evenings. We have as well other scenarios that we have run, as my colleague Dr. Schott has mentioned, the demand turn up in the UK market, the electricity peak demand reduction corresponding to the EV chargers, and the fast frequency response, which corresponds to one of the products in the UK market as well. And now I'm going to finish by giving the floor to my colleague Igor Prevosnikov. Thank you very much.
So hello everybody, I am Perevozchikov Igor from Nobatec in a French company, and I am responsible of the French pilot site in the context of the Dr. Bob project. So the French pilot site is composed by 3 independent recent buildings. The first one is the training center of the Compagnon du Tour de France, which is a training center for building trades. So hosting office rooms, classrooms, and technical workshops. The second one is the headquarters of Nobatec Info company, which is mainly office building with some laboratories. And the third one is the Arkinova Business Incubator building, recently constructed, which is dedicated to sustainable and bioconstruction startups. So the particularity of this building is that it is the positive energy building, which generates more of photovoltaic energy. So photovoltaic panels are located on the roof of this building than it consumes. So some particularity also of the French pilot site is that it is the pilot site with 3 independent owned by different owners building, and also managed by different building managers. So ANDRBOB solution architecture implemented at the French pilot site is presented at this slide. We have combined 3 building management systems infrastructures into one local network by installing 2 VPN tunnels between GA building BMS infrastructure and Novatec building BMS infrastructure, and the same for FCMB building. So this configuration allows us centralized management of building assets of these BMS systems and centralized data collection, so meter readings collection. So the local energy manager is installed also locally at the supervision PC of the Novatec BMS systems. It interacts with 3 building management systems and forwards the data up to the other blocks of solutions, which are the DEMS and consumer portal, into the cloud. So consumer portal allows us to interact with the building managers of each building and corresponding building occupants. So when a new incoming demand response event is generated by ANDRBOB solution, consumer portal send a notification to all 3 building managers requesting them to opt in or opt out building assets to participate into these events. Building managers proceed to opt in or opt out building assets, and in the case when they opt in some building assets, they inform about the corresponding building occupants. Once demand response event is finished, the building occupants of all building participating receive a notification with a request to give their short feedback about their active or passive participation into the last demand response event. So we have decided to run 4 different scenarios at the French pilot site. So our 3 scenarios are based on a simulated signal generated by several blocks of ANDRBOB solution, and these are the scenarios 3, 4, and 5. And one scenario, which is the first scenario, is triggered by a real signal, which is the peak period 1 signal from the French capacity market. So the forecast regarding the peak period 1 are available publicly on the website of French transmission operator RTR. And so we used this signal to demonstrate the potential of controlling assets in block of buildings in response to this signal. So in the scenarios 1, 4, and 5, the scenarios were dedicated to all the buildings involved into the French pilot site. And into the scenarios 3, there was only FCMB building which has been involved. So FCMB building is heated by 2 heating energy sources. The first one is gas-fired boiler, and the second one is a wood chips boiler. And wood chips are considered as renewable local source because it is produced during practical works by the apprentices of FCMB training center. And so the idea of the scenarios 3, it was to proceed to gas demand reduction by switching from gas-fired boiler to the wood chips boiler, using some techniques of preheating and changing ambient temperature set point. So the building assets involved into the scenario 1 and the scenario 4 are the same. It's all 3 buildings. So there are mainly HVAC building assets, so heat pumps, ventilation, cooling systems, and also occupants' laptops. We engaged occupants to make shifting of energy of charging their laptops to another times of the day. And so it was operated by shifting and shading the load consumption and preheating techniques. And the scenario 5, so name it virtual microgrid or sharing of electric energy inside the demonstration site area, has been triggered by the excess of energy produced on the BI building. So when locally generated energy totally meets and excess electricity demand of BI building, this excess of energy has been virtually shared with other 2 buildings of the block of buildings. And the idea of this scenario was to absorb this excess of energy to better meet building consumption, to better match, building consumption to local PV energy generation. And so the assets participating here, it was electrical vehicles, some big loads of the buildings, and also heat pumps and ventilation assets. So it can be distinguished in 2 kinds of scenarios at the French pilot site. Firstly, cold period events, which are the events of the scenarios 1, 3, and 4. And secondly, the warm period events, which are the events of the scenario 5. You can also see that we have implemented the most of events, but we expect also some events in December months. So for the moment, the results showed here are intermediate results. These are not the final results of the French pilot side, but so you can see here. So the impact for building managers. The optimization criterion for building managers of all 3 buildings was firstly the financial savings. The second impact for them, it was a raise of awareness between building occupants about energy efficiency, demand response, and sustainability in the buildings. So you can also see here that the impact, quantitative impact from the scenario short duration, which are the scenarios 3 and 4, has been less important than the impact from the scenarios longer duration 1 and 5. So what are the lessons we learned from this demonstration? Firstly, what are the buildings which could participate in the demand response programs? So these buildings should be highly instrumented and be equipped with building management systems to allow monitoring of building assets and meter readings collection. Secondly, and what programs, demand response programs, the buildings can participate. So the blocks of small office buildings can participate into almost all programs which don't require very fast and immediate action on building assets. The most of action has been made manually by building managers through BMS, but we also tested some automated action by the LEM directly to the assets of the building. Building managers in the small buildings are not only playing the role of building technical building management, they have a lot of other missions. So they should be notified at least 24 hours before event begins. And the last one, engagement of occupants into energy shifting actions depend a lot from the local context of building. In the buildings with some vertical hierarchy between building occupants, the engagement of occupants works better than in the buildings without this hierarchical relation between them, like in the BI building. And so during the French demonstration, the DRTRL level of the French pilot site has been raised from the level 1 to the level 3. Thank you for your attention, and I pass the relay to my Romanian colleague, Andrei Sela.
Sorry, Andrei, can you unmute yourself?
I didn't notice that I was muted. So we have 4 locations in our site. They are in different parts of our city. So we are in Cluj-Napoca in Romania. This is the European Capital of Sports this year. So the 4 locations comprise these 2 faculties, the electrical engineering faculties and the building services faculties. A student dormitory with 2 large student hostels and restaurant. And then we have a swimming pool complex. All these buildings are comprising around 4,000 occupants in all of them. What we have done in preparing the project was to implement a building energy management system. You can see in this slide that we have the interface comprising all the 4 locations in the BMS, with which we are monitoring the energy use, the electricity use in all the buildings, both at the general level and on some sub-users, energy users. We also integrated the building energy management system into the architecture of the project, so we are communicating with the local energy manager, with the demand energy management system, and with the consumer portal. It is very important, the last consumer portal instrument, because through this website we are communicating with the occupants in the buildings. Another fact is that we installed TV monitors at the entrance of the buildings so that the occupants in all the buildings to see the real-time energy use of the buildings And we done this because most of the occupants in these buildings are engineering students or already engineers or academic staff, which is accommodated with electricity and energy domain. And using these monitors, we are also communicating when the events will occur and what is the visual impact of each demand response event. So during the test period of the project, we implemented a number of events on each scenario we defined for our own buildings. So we have the virtual critical peak period pricing with automated control, which we are applying in all these buildings. The second demand, the scenario is explicit demand reduction in the student dormitories, which is a manual scenario, because in this second scenario, we are requesting the students and the other occupants in the buildings to contribute and to voluntarily shift or switch off some of their appliances. And this is, I think, the most provocative scenario in demand response which we implemented, because at each event we have to request them to involve, and we are counting on the number of the students that are involving. And the third event, it's virtual time of use tariff, which consists in scheduling some loads in the buildings. What you can see next is that we have some visual results of the events. Here with Red Soko, you can see the result of one event which was implemented in the swimming pool complex. And the other slide, it's a visual result of the demand response event which was implemented in the faculties of electrical engineering. So as it looks like in the graphs, the events were with an impact, had an impact. Then we selected some of the events so as to have some lessons learned from them. They are in different times during the year, in different hours during the day, and in different locations. So the first one you can see with red marked, it's that when we started to implement events in the student dormitories, in that first evening, we had also a football game at the same time. So the students were more concerned about the football game, and they also asked us to lend them the TV monitor, the TV screen, to see the football game. This was a lesson for us because we learned during the year how to talk and how to communicate with the students so as to involve them. After that, the next event involving the students, we prepared some instruction on each floor of the student hostels so as to attract them in this project. Then we also concluded in all the buildings that the administrators of the buildings have a decisive involvement in these events. Having, we think, a significant number of events, we also computed, and this is only preliminary data, the impact of the events in terms of energy saving, electricity saving, peak power reduction, and cost savings. And what you can see in this slide is that for all the locations in our site, we extrapolated and evaluated cost saving of around 16,000 euros per year as a cost saving resulting from the benefits of the demand response in blocks of buildings project. And we also performed the cost benefit analysis, which you can see in this slide. We inserted as an input data the cost of the building energy management system and the revenue that we calculated, that we evaluated for the whole year. And what we can see is that this investment in demand response in buildings can be very attractive. For our site, it proved to be. And we've done this because in Romania, in our country, the demand response potential, it's rated at around 100 million euros per year. So the attractiveness of this business model is very high if it will be implemented on a large scale. So this is what we have done in our site up to now. We are preparing to finish the implementation of the events in December. And we also raised the DRTRL from the first level to the second level by implementing the building energy management system, by controlling manually or automatically some of the assets, the HVAC especially, and by integrating this BMS into the architecture of the project. So this is what we have done, and I will pass the control to the Italian side to my colleague, Federico. Thank you.
Hello, thanks, Andre. I'm Federico Calluzzi. I'm running the scenarios and the project for the Italian pilot side. I'm the energy manager of a hospital. The name is Fondazione Poliambulanza, which is a private non-profit hospital located in the city of Brescia, which is a city in north region of Lombardy in Italy. The dimension of the hospital, let's say for Italian standard, is like a mid-sized hospital for dimension and for the number of patients treated. So we are close to 700 inpatient beds. Between patients, outpatient employees, and visitors that come every day here in Poliambulanza, we have around like a little bit more than 5,000 people that walk through the hospital every day. Our energy consumption, our yearly energy consumption is shown on the slide. And in the last year, actually during the second year of the Dr. Bob project, we switched most of our energy consumption from electric energy to natural gas, because we install a tri-generation, so a CHP, that provides electric energy, that is participating to the project, of course, and provides electric energy, heat and cooling capacity to the hospital. Beside that, so beside electric energy and natural gas, we also we are connected to the district heating, so we have a high consumption also of warmth capacity from the district heating network of the city of Brescia. Within the property of Poliambulanza, we have 4 buildings. The first building is the first one actually was built in 1987 and has 30,000 meters square of net floor area. Then we have the one is green and blue. The first one is the patient building, and the blue is the operating room building. Those are a little bit the newest building of the hospital, and they are almost the same size, so around 9,000 meters square. The operating room building, the blue one, is what we call a high technology service building. We have there 10 operating rooms, a new pathology anatomy laboratory, sterilization central department, delivery rooms, and intensive care. So it is the building that consume, let's say, a lot of energy. I mean, the energy it's quite high per meter square. The last building in red is the research center. They have research on stamina cells there. The building also hosts a few classrooms and that are used for training courses. The hospital was built in 1997 and was already equipped with a building management system, so a BEMS, but which main purpose was to introduce an automatic and remote control of the assets of the hospital for the safety basically and the comfort of the occupants. So the BEMS didn't have any meter connected and didn't have any specific tool to monitor the energy. So what we did during the project was installing several power meters for electric energy, gas, and heat and cooling capacity, and a software that was able to collect, record, and display all the data for the definition, for example, of a baseline. So the software also display instant values and record values every 15 minutes that actually for the project are sent to the LAM for through an FTP server. And as I said, thanks to those thanks to the data, we can define what is our baseline and monitor the effectiveness of the demand response events. The software that we installed, so the energy monitoring software, can read values actually also from the BEMS. So the few values that we have on the BEMS from regarding energy or temperature can be displayed on the energy monitoring software, but all the inputs of set points and the whole machine are controlled manually on the BEMS. So for safety reason, let's say for due of the kind of service the hospital have to give, and also of the lack of explicit demand response here in Italy, all the scenarios were run manually by the energy manager team. So an event is created and then is displayed, and so a notification is sent by the consumer portal, and then take action actually the event. And as I said, is all manual action. So we involve the people from the say technical department of the hospital, like maintenance, that actually run the scenarios, changing the setting on the BEMS and also locally on the machines, for example, chillers. We implement 4 different scenarios for the project. The first one is the control of the electrical chillers. We lower their capacity during demand response events, and we use the inertia basically of the water in the hydronic circuit. So we use that water as a thermal storage basically. In this scenario also, to be able to have a longer energy reduction in terms of the time, we pre-cool the water by 1 or 2 degrees Celsius before the event. The second scenario is shedding of small loads. So we ask all the employees of the hospital to lower energy consumption by turning off PCs, monitor, printers, or light or anything. It's like easy to reach for them for the period of the event. Scenario 3 for us is trying to lower the consumption of important loads. For example, the food carts. So the food carts are used at lunchtime to deliver food to the inpatient, and we use them as a basically a thermal storage. So we pre-warm warm a little bit later the food carts, so we can switch the power consumption of those say asset 30 minutes or before or after in order to have like an event that lasts 30 minutes. On scenario 4 involves the new power plant, so the tri-generation. So the CHP provide both cooling and heating capacity to the hospital, and the heat recovered by the engine can be used in an absorption chiller or directly with a heat exchanger to have just to warm up the hospital. In case of an event, what we can do is switch all the warm capacity or warm power of the CHP to the absorption chiller, so we reduce the energy, the electric energy consumed by the chillers. So what we do basically in this scenario is switching from a use of electric energy to a use of district heating or natural gas. We run a few scenarios. Most of them we run for scenario 1 and 4 that are the one that we can control a little bit better from the BEMS, so are the ones a little bit more automated. And we run them both in like summer season, then let's say now in the last few weeks, with of course different results in terms of power shedding. So after setting up all the scenarios, trying to run them a few times, we analyze also the response of the asset involved. And I'm talking more about the electrical chillers, but also all the equipment cooled down by them. So not just the air handling unit, but also the medical equipment like MRI. We found that the best combination to have a longer and higher energy reduction, so a better demand response, was to combine the scenario 1 with the scenario 4. So lowering the electric energy of the chillers and switching the cooling generation from electric energy to gas consumption or district heating. These in the slide are the assets involved in these two scenarios. So on the right, the power plant, and on the left, the electrical chillers. And it's also display all the data that we have to monitor during this scenario in order to make sure that all the other equipment is, let's say, run safely inside the hospital. Here we have, I have just two slides that reported what we recorded during the those scenarios. So as you can see, this scenario was run in June between 11 and 12 in the morning. So what we did, and this is on the right image in the point B. So what we did was pre-cooling a little bit the water of the hydronic circuit of the hospital. So we switched the set point of the chillers from let's say what was like 7 degrees, the normal set point, to 5 degrees, and we hired that set point when the event started. So we put it on 8 degrees. So that point, let's say C, that is displayed on the right image. So we were able to record actually sensitive reduction of electric energy. And at the end of the event, so at 12, we put the setup back to the chillers to 7 degrees. That is the nominal value for electrical chillers. So in this event, that day, we were able to lower by 20% the peak power demand. This also is let's say the same event that we were able to run on October. So also in this case, you can see and let's say the electrical power chiller is the yellow line in the graph. The electric energy from the grid, so the total consumption of the hospital, is the light green. And you can see that when we run the event, in this case around 1 to 2 p.m., so we record a decrease of energy consumption by 33%. So what happened is that we pre-cool, like in the event before, we pre-cool the water with the electrical chiller, and during the event we switch the cool production from electrical chillers to absorption chillers. So that's why the cooling capacity from the absorption chiller went, let's say, very high during the event. In this case, we were able to reach minus 33% of the peak power demand from the network. So what we learned in these months of running the scenarios is that the more people involved, the less the power reduction is predictable and replicable. So that means that, for example, in scenario 2, where we ask all the employees, all the occupants of the hospital to turn off the equipment, it's a little bit hard to predict exactly how much will be the reduction of energy. And also we saw that not all the time we reach the same values. Also, we learned that a full automation in the control of air handling units by the BEMS makes the demand response more effective. So, for example, in scenario 1 and 4, that we are a little bit more advanced in automation, we reach higher values of energy reduction. And the last thing is that the design of the plant architecture and machine can help to reach better results in energy reduction. So that means that not always we were able to run scenarios like the number 1 or number 4 or with involved chillers, because we weren't able to change the setting of the machine as fast as we needed. Also for, let's say, the safety operation of the machines and also maintenance problems, say. So that means that in a design of the new asset eventually that we will install in the hospital, we will think also about the readiness, the level of readiness for demand response. In this last slide, it's just shown the implementation of demand response readiness, and let's say also thanks to the project we reach let's say partially automated level. I will give the floor now back to the moderator.
Okay, thanks. Thanks to Tracy Crosby. Thanks to all the Dr. Bob project team, and very, very high level technical quality of your presentations. And in fact, we received a lot of questions, so we are running some minutes late, but please let's reserve some minutes more for the questions. To Tracy, I'll ask mainly to Tracy. I've grouped and matched the questions because really a lot of one. And the first one is, what is the ideal building typology to be implemented, and how much scalable and replicable is your solution? As we have seen demo cases applied on block of buildings, and we mean with block of buildings a group of buildings under common governance. So, for example, could you apply the solution to urban settlement or at neighbor level? And in this case, you think that the barriers are more connected to the technology applications and the availability of the solutions on the market, or are more related to the governance of the process?
That's a lot of questions in one. In the Dr. Bob project, we've mostly applied this in, well, we've applied this in what we think of as commercial buildings, that's non-residential buildings in English speak. And we found that really, while there are some issues in relation to needing to implement more up-to-date building management systems and metering with a greater level of granularity in the buildings, that one of the key issues related to the implementation of demand response in non-residential buildings relates to the governance of those buildings and the buy-in of both the facilities managers and the people occupying the buildings. Because even if you're at TRL level 3, and you have automated control in automated actuation in order to be able to automatically control chillers and heating and ventilation systems, you still need buy-in from the facilities managers, and you still need buy-in from the occupants, because they are going to notice a change, maybe in temperature or something else. So I think it's very, very important that we have if you think about it as the social network set up, as well as the technical networks, in order to implement demand response. I also think that the solution that we've developed could be applicable within the residential sector. And I think it does offer a way forward for the aggregation of demand response in blocks of buildings, be they blocks of buildings such as a university campus where we've tested and piloted the current ANDRBOB solution, or be they a block of a virtual block of buildings, say buildings owned by a municipality or local authority, which could be scattered across a city rather than being next to each other. Do you think that's addressed all of the questions, or is there something outstanding?
We have other questions. Another question is about cost benefit. We already listened about economic cost benefit and concrete profits. The other question is about which are the main co-benefits that you have observed in your demo cases, if any, in terms surely of energy savings and flexibility towards the energy grid, but also such as awareness on user behavior and comfort for the occupants. And also, which is the role of the occupants, is a welcome and active role, or your solution is dedicated mainly to building manager?
Okay. Okay, whether or not the solution is dedicated to the building manager or not largely depends on the type of building. In most of the pilot scenarios that have been run, it has involved the users or the occupants of the buildings also responding to a demand response request. And we have not found so far that there have been complaints about decreased thermal comfort in the building, but we have also not found any compliments about increased thermal comfort at the building level. Currently, we're analysing the qualitative data that we've collected from interviewing the occupants of buildings that have taken part in the demand response pilots, and we don't have a definitive answer yet to the questions of how it impacts on the occupants of buildings and what the added value might be for the occupants of buildings. However, I do think, given the amount of buy-in that you need from the building occupants and the building owners, that it's very important that we try to address potential added value for building occupants of taking part in demand response, particularly in the case of those types of buildings where the occupant is not responsible for the energy cost.
Perfect. And we have another specific question on the nature of explicit and implicit reduction of energy, and if there are any examples available for applications. I don't know if this right addressed to you, Tracy, or to someone of your staff.
Okay, let me think. Well, if we're talking about, are we talking about explicit and implicit types of demand response, or are we talking, okay, because an explicit demand response program is where you're paid a certain amount of money in order to promise to reduce your energy consumption. Yeah, an implicit demand response program is where you have a time of use tariff, or an implicit way of reducing your demand. And in the scenarios that we have run, we have tested both explicit and implicit demand response products. So does that answer the question? I'm not sure.
Okay, we received another questions, but maybe it's really
Okay.
We are running too late. So we can send the the answer to your questions by email, and we will be glad to give you further information via mail about this very interesting project. So thanks again to everyone for attending, and thanks for presenting this project. And again, I renovate the appointment for next webinar at the mid of December, and stay tuned on Build Up.
Thank you very much. And thank everybody for attending.